This lesson's about the force that an external magnetic field exerts on a moving charge, and here are your objectives. So first, let's imagine that we have two bar magnets, and I'm just showing the end of them here. This is the north pole of one, and this is the south pole of another. And so because the magnetic field points in the direction that the north pole of a compass would point, if we draw our magnetic field lines in between them, the magnetic field would point from left to right. And here it would be a little bit curved. Now, if we had a charge that was sitting here stationary in the magnetic field, because it's a stationary charge and magnetic fields affect moving charges, this would feel no magnetic force at all. So a stationary electric charge doesn't feel any force in an external magnetic field. But if it had a velocity, let's say it was moving up like this, now it's a moving charge, and moving charges experience magnetic forces. So once it's moving, it would now feel a magnetic force. And that's what this lesson is about, figuring out the magnitude and also the direction of the force that this will feel. It turns out in this case, as we'll see, that the force is actually into the plane of the paper or into the screen. And that means that we need ways of showing forces or fields in 3 dimensions on a 2-dimensional surface. So we're going to use an X to show a field or a force that's going into the paper, and a dot to show one that's going out of a paper. And you can think of this as being like the fletching and the arrowhead on an arrow. So if you're looking at the front of an arrow is coming towards you out of the paper, it would look like a dot. And if you're looking at the fletching at the back, it would look like this X. Using those symbols, this would be what a magnetic field pointing out of the paper towards us would look like. So in other words, if we were to take this bar magnet with the north here and push it away from us into the screen and swing the south pole here towards us out of the screen, we would get a magnetic field that looks like this. And again, we could pass a charge through it, and if it was a moving charge, it would feel a magnetic force. And in this case, as we'll see in a moment, the force would be pointing downwards. Now, from experimental observations, we can see that the force is proportional to the charge. If you had a 2 Coulomb charge, it would feel twice as big a force in the same external magnetic field as a 1 Coulomb charge would. We also see that the force is proportional to the magnetic field strength. If you were to double the magnetic field strength, for example, by putting another identical magnet there, you'd get double the force. Now, the units of the magnetic field strength are called the Tesla, which we give the symbol capital T to. And just to note that 1 Tesla is a very, very big magnetic field. The Earth's magnetic field is about 10 to the minus 4 Teslas, and that's actually also given another name. It's called the Gauss, because a Tesla is such a big unit. So we'll often see small fractions of a Tesla for our magnetic field strength. It also turns out that the force is proportional to the speed. Double the speed of the particle and you double the force that it will feel in the same external field. And the direction that it's moving matters as well. The relative orientation of the magnetic field, which I'm writing here as the B field, the relative orientation of the magnetic field and the particle's velocity affects the magnitude of the force. Not just the direction of the force, but the magnitude of the force as well. And the force is always perpendicular to both the magnetic field and the velocity of the particle. So what does that mean? It means that if we were to change the orientation of either of these particles' velocity, we would change not only the orientation of the force that they would feel, but also the magnitude of the force that they would feel. And we'll explore that more in a moment. Now, putting all these together, it can be determined that the magnitude of the force is equal to the magnitude of the charge particle multiplied by its speed, multiplied by the magnetic field strength, multiplied by the sine of the angle in between them. Theta here is the angle in between the particle's velocity and the magnetic field. In both of these diagrams, that theta is equal to 90 degrees, and that can be hard to see at first. Easier to see over here, perhaps harder to see over here, but the angles in both cases are 90 degrees. In this case, if I were to turn the particle's orientation like that, now it's no longer 90 degrees, but here it is. So the formula that gives us the force in newtons is equal to the charge multiplied by the speed multiplied by the magnetic field strength multiplied by the sine of the angle in between them. That gives us the magnitude of the force, but what about its direction? Well, let's redraw the second situation that we drew on the previous page. We've got a magnetic field that's pointing out of the page towards us, and we're going to send a positive charged particle to the right through that field. So we're sending it this way. Now we need to use something called the right-hand rule for a moving charge in an external field. What we're going to do is we're going to point the fingers of our right hand in the direction of the velocity, fold them in the direction of the field, and then our thumb is going to point in the direction of the force. So let me draw what my hand would look like. So if I wanted to point my fingers to the right, because that's the direction of the velocity of this positive charge, there's two ways I could do it. These are both pictures of my right hand, one with the back of my hand facing outwards and one with the palm facing outwards. So both of these are right so far because I'm pointing my hand in the direction, my fingers in the direction of the positive charge's velocity. However, if I now want to fold my fingers in the direction of the magnetic field, there's only one way I can do that. I can't fold my fingers in that direction if my hand is oriented like that. But if my hand is oriented like this, I can just bend my fingers in towards my palm and they'll be pointing out of the page in the direction of the magnetic field. So now I've changed the drawing to try and show that. So I pointed my fingers in the direction of the positive charge's velocity, folded my fingers so that they were now pointing in the direction of the magnetic field here out of the page, and that leaves my thumb pointing downwards, and my thumb is telling me the direction of the magnetic force. Once again, positive charge moving to the right, I point my fingers to the right, the magnetic field is pointing out of the page, so I bend my fingers so they're pointing out of the page. There's only one orientation in which I can have my hand to do that, this one at the bottom, and that leaves my thumb pointing downwards, giving me the direction of the force. Now it's important to note that this is for a moving positive charge. If I use this for a negative charge, it'll give me the opposite direction of the force, so I just need to flip it around. Now we can capture both the sine theta part of the equation and also this directional aspect that we've used the right-hand rule for using a mathematical notation called cross product notation. We can rewrite the formula above, QVB sine theta, like this. The force, and notice here that we've got the little vector arrow because the equation is actually going to capture the direction as well. The force is equal to Q, the charge, times the velocity. Again, we've got a vector arrow, and this big multiplication sign, this is the cross product sign. So QV, we read this as cross B. And again, we have the vector arrow because the direction is in here. Now, this mathematical notation means that the magnitude of the force is exactly what we said before, QVB sine theta, but it actually also captures this right-hand rule part of the direction. Because when you see something written like this with a cross product, this is the thing that we are pointing our fingers towards. So we are pointing our fingers in the direction of the velocity. Then we are folding them in the direction of the thing that comes after the cross product sign, and that leaves our thumb pointing in the direction of the force. And I'm showing this to you now because you'll see it again when we look at the force that an external field exerts on a current carrying wire, and we can use this notation to help us remember that as well. You don't need to use or remember this notation if it's not helpful for you, but for some people this helps remember everything in one go. Let's look at one more thing, and that's the circular motion of a charged particle in an external magnetic field. Let's say that we had a positive particle here moving to the left, so its velocity is to the left. And the external magnetic field here, as you can see, points into the page, into the screen. So if you use the right-hand rule, you point your fingers to the left here, fold them into the page to indicate the direction of the magnetic field, and that leaves your thumb pointing downwards, showing that the magnetic force is downwards. Now the force is perpendicular to the velocity, so this force, this magnetic force that's downwards, doesn't do any work on this charge and doesn't change its kinetic energy, doesn't change its speed. What it does do is it bends its trajectory so that at some later point, now it's moving downwards. So I'm using blue here for the velocity. This was the velocity, here's the velocity here. And now if you use the right-hand rule again, point your fingers down, fold them into the page, your thumb is now pointing to the right. So the force is pointing inwards. That's going to again turn the trajectory of the particle so that at some later point it is down here and it's moving to the right. And again, because the force is perpendicular to the direction of motion, it's doing no work, and so the particle is not changing its kinetic energy, not speeding up or slowing down. Repeat the process with the right-hand rule and you get a force that's pointing upwards, and that's going to turn the particle's trajectory so that at some later point it's going to have curved up here and now its velocity is upwards. And repeating the right-hand rule, now we see that the force is pointing to the left. And what we see, therefore, is we have circular motion. We have circular motion where the centripetal force is given by the magnetic force. In other words, mv squared over r is equal to qvb sine theta. And in this case, because the velocity is always in the plane of the page and the magnetic field here is pointing into the page, the angle between them is 90 degrees, and sine of 90 degrees is 1. So this cancels out, and we get mv squared over r is equal to qvb, and we can rearrange that to find things like the radius of curvature. Again, note that the force is always perpendicular to the velocity, and therefore the force does no work, so there's no change in kinetic energy or speed of the particle. And also, the force we saw here always points towards the center of the circle. Putting those two things together, then, we've got uniform circular motion, meaning circular motion at a constant speed. So a charged particle moving in an external magnetic field, if it's got enough room to do so, it doesn't run out the end of the field, will exhibit uniform circular motion. And that's an introduction to the motion of a charged particle in an external magnetic field.